Shooting that. Okay. So 17.1, we talked about what vector fields are. Vector fields assign vectors to points in space or in the plane. Frequently used to model velocity fields or force fields. 17.2, we talked about line integrals. Line integrals are a generalization of single variable calculus integrals, but instead of integrating over an interval, we're integrating over a one-dimensional curve in space or in the plane. And just like the integrals you learned back in single variable calculus, line integrals can be used to calculate a wide variety of quantities. One of those quantities being work in circulation. And so we have that from 16.2. Work or circulation, we could express the integral. We'd look at f dot t hat ds. How much force is in the direction you're going times the distance you've gone, and we add all that up. But then after we went through some of the algebra there, we could write this as f dot dr. That would be our work integral. And so today we're going to talk about a way to calculate these integrals, work integrals, in the specific case that f is a gradient field. So if f is a gradient field, we're going to talk about a way we can get around this. Okay, but before we get into that, we have to talk about what it means to be a gradient field. So given a scalar function phi of xy, so this is our new generic phi here. So phi of xy is a scalar function. It takes a point to a real number. And we talked about the gradient of phi going back to chapter 14. It is a vector field. So the x component is the partial with respect to x. The y component is the partial with respect to y. All right? And this generalizes to 3 space. So we actually looked at these gradients a couple chapters ago. And so the question is, okay, if you have a scalar function, you can create a vector field by taking the gradient. The question is, are all vector fields gradient fields? So let's take a look at this field here, f of xy. The field 2y comma minus x. This is one of these rotation fields. And the question is this a gradient field? Okay, well, if this were a gradient field, then that means this field would look like the partial derivative with respect to x, comma, partial derivative with respect to y, which means that your phi x would have to be 2y, and the phi y would have to be minus x. So if phi x is 2y and phi y is 2x, we can check to see if the mixed partials are the same. So if I look at phi xy and phi yx, what do I get if I take the derivative of 2y with respect to y? What do I get? If I take the derivative of minus x with respect to x, what do I get? Minus 1. And what's the problem here? Fubini's theorem said if phi xy and phi yx are continuous, then they have to be the same. These aren't the same. All right? So phi xy does not equal phi yx. So this leads us we have a contradiction. So that means that the field f can't be a gradient field. Oh, okay. Can you look off your computer, Abby, or no? Oh, okay, cool. All right. Okay, so we got some vocabulary here. If the field you're given is a gradient field, we call this function here phi. We call the field a gradient or conservative field, and the scalar function phi is called the potential function for the field f. So I know a lot of you are physics fans. You've maybe heard of things like gravitational potential. That's the same sense of the word potential here, and we'll see that here in a minute. So how do we determine if a field is conservative? Well, we have the following theorem. Oh, I can imagine. I mean, it's a good one. Suppose you got a two-dimensional field where m and n have continuous first partials. All right. F is conservative if and only if my equals nx. So f is conservative means f is the gradient of something. So let's be a little more. Let's spell this out. So there's that. So f is the gradient of something if and only if my equals nx. So this is called the exactness criteria. Now, this is an if and only if statement, meaning if f is a gradient field, then my equals nx. The more powerful part is if my equals nx, then it's a gradient field. So this is how we're going to check. Now, to show the one direction of the implication, so if f is the gradient of phi, right, then mn is phi x phi y. So my would be phi xy, and nx would be phi yx. And so my equals nx is equivalent, I mean, that's Fubini's theorem, okay? To go the other direction requires a little bit more work, which we'll see later, okay? But this is how we're going to check to see if a field is conservative. So, is f conservative? Well, here's how we'll do it. We'll identify the m and the n, and we'll check. Does my equal nx? Right? That's how we're going to check to see if a field is conservative. So, for example, we got a field here, f. Use the exactness criteria to show f is conservative. So once again, we're going to identify the m and the n. The m is always the x component. So we will look at my. So we're looking at the derivative of the x component with respect to y. So once again, we're looking to see if the mixed partials would be the same, is really what we're doing here. So if I take the derivative with respect to y, what's the derivative of e to the xy with respect to y? Yeah, so derivative of e to the something is e to that thing, times the derivative of that thing with respect to y, that'd be your x plus. And then what rule would I have to use here for the second term? So I'm going to take the derivative of this with respect to y. What rule would I need? Yep, product. I take the derivative of the first factor with respect to y. That's going to give me an x. Plus I take the derivative of the second factor with respect to y. That would give me an xy e to the xy times another x, so there'd be an x squared. So I'd have 2x e to the xy plus x squared y e to the xy. So that would be my my. And now I have to check to see if I get the same thing if I take the derivative of n with respect to x. And n is always the y component of the vector field. So n is the y component of the vector field. So nx means I got to take the derivative with respect to x. What rule do I have to use here to get started? That's your product again. So derivative of the first factor with respect to x is 2x times the second plus x squared. Derivative of e to the xy with respect to x would be e to the xy times the derivative of xy with respect to x, which gives me my y. And sure enough, my equals nx, which means the field is conservative. So if the field is conservative, then that means there is some scalar function phi. So the field is the gradient of phi. And so now the question is, find the potential function phi. And there are a couple different ways to do this. Okay. Both ways start off with, all right, f is the gradient of phi. So we equate components. Partial derivative of phi with respect to x would be m. And the partial derivative of phi with respect to y would be n. So phi x would be the x component of the field. The x component of the field would be the partial of phi with respect to x. So that's going to be e to the xy plus xy e to the xy. And the partial derivative of phi with respect to y has to equal x squared e to the xy. So what we have here, technically speaking, is we have a system of partial differential equations, which sounds pretty intense. But there's a couple different strategies to this. One strategy is integrate the first equation with respect to x, integrate the second equation with respect to y, and try to match up pieces, parts. The method that I like to show students, and I don't care what method you use, but the method I like to show students is more methodical. So the method I like to use is we start with one of these equations. So we either want to integrate phi x with respect to x, or we want to integrate phi y with respect to y. Okay. So which one would you want to integrate? Would you want to integrate the phi x with respect to x, or the phi y with respect to y? Yeah, let's do y. Because if I'm going to do the x, I'd have to do parts or whatever. So we're going to do phi would be the integral of phi y with respect to y. So phi y is x squared e to the xy dy. And as far as y is concerned, x squared is just a what? Constant. So yeah, this would end up giving me x e to the xy plus a constant. Now the thing about this constant is it's a constant as far as y is concerned, which means it could be any function of who? It could have a what in there? Yeah, it could. Well, no, not a y, because we integrated with respect to y. It's a constant as far as y is concerned. In other words, if I took the derivative of this with respect to y, I would get back to here. But anything that has just x's in it, yeah, would drop out. Okay, so this is what my phi looks like. Now to figure out the dependence on x, if any, I would then turn around and take the derivative with respect to x. Taking the derivative with respect to x, that would require the product rule. So I'd get an e to the xy plus x times derivative e to the xy with respect to x. So e to the xy times y plus c prime of x. And now I'm going to match this up with the x component of the field. So I get e to the xy plus xy e to the xy plus c prime of x equals the x component, e to the xy plus xy e to the xy. And I can see what happens that I've got that term accounted for. I've got that term accounted for. So the c prime of x would be 0, which means this constant, which could have had x's in it, really is just a plain old what? Constant. So there is no dependence on x in that. And so our potential function phi of xy is x e to the xy plus a constant. And then the ultimate check for this is you calculate the gradient of phi and show that you get the field f back. So the method here is called the method of successive partial integrations followed by partial differentiations. What we're doing here is we're trying to determine what phi looks like one variable at a time. So we integrate one of the partials and then take the derivative of that answer with respect to the other variable to try to pin down the dependence on that second variable. Does the logic make sense? It's very methodical. And we'll do more examples like in other dimensions here in short order. Okay, 3 dimensions. So this exact same concept extends over to 3 dimensions. So let's think about it. Let's say you got a field F. M and P, and this is supposed to be the gradient of some scalar function. That would mean that phi x would be m, phi y would be n, phi z would be p. And assuming m, n, and p all have continuous first partials, we can use Fubini's theorem to figure out what the exactness criteria looks like here. So for example, we know that phi xy would be phi yx. So phi xy would be my, phi yx would be nx. Well, that's the same exactness criteria for 2 dimensions because we're looking at x and y again. Phi yz would have to equal phi zy. Phi yz would be nz. Phi zy would be py. So those two have to be the same. And what would be the last thing we'd have to check? Phi xz would have to be phi zx. So what would that be? Phi xz would be what? What would this be equivalent to? So what would phi xz equal phi zx? What would be that? What would be the components? Yeah, phi xz, that would be mz. Phi zx would be px. So this is the exactness criteria here. And f is conservative if and only if we meet the exactness criteria. All right, so here's a field. M, remember that's always the x component, that's z. N is the y component, minus z cosine yz. P, z component, x minus y cosine yz. And let's check. Let's look at my and nx. So I take the partial derivative of m with respect to y. There's no y's. So that partial derivative is going to be what? 0. Now I go to take the derivative of n with respect to x, and I see that there's no x's there, so that partial derivative is also what? 0. So these are both 0. So my equals nx, done. Excuse me. Now we'll look at the partial derivative of m with respect to z. The partial derivative of m with respect to z is just going to be what? 1. And that has to be, so that's the x component with the derivative of the x with respect to z. Now I need to see the derivative of z with respect to x. So I take the derivative of p with respect to x. And once again, I got x here. All this stuff, as far as x is concerned, is just a constant. So what's the derivative of p with respect to x? 1. So mz equals px. And then last but not least, I'm going to check the derivative of the y component with respect to z and check that that's the same as the derivative of the z component with respect to y. So nz to do nz, this requires what rule? Product. So the derivative of the first with respect to z would be a minus 1 cosine yz. Then I'd have a minus z times the derivative of cosine of something. The derivative of cosine of something would be a negative times that negative would be a positive. Z sine x, excuse me, yz times the derivative of yz with respect to z. So I give you a y. So I guess we'd end up with that. So that would be your nz. And now we got to check that that's going to be the same as the partial derivative of the y component with respect to z. Excuse me, of the z component with respect to y. So now I'd be looking at py. So the derivative of x is going to be 0. Once again, what rule do I have to use here? So, yeah, product again. So the derivative of y with respect to y is, we got that minus 1 there. And then we're taking the derivative of, we have minus y times the derivative of cosine, which would be minus sine. So that'd be a plus y. And then the derivative of yz with respect to y would be z, and so that tracks. So once again, when I mentioned how Chapter 17 is a comprehensive review of all things in the course, here we are taking partial derivatives and looking to check to see that the mixed partials are the same. Right? So it's a complete callback there to the early days in Chapter 14. Does this make sense? Do you see why we're checking what we're checking? The derivative of the x component with respect to y has to equal the derivative of the y component with respect to x, so on and so forth. All right? Not only is that a necessary condition to be a gradient field, it's sufficient. All right, now we got to find a potential function. So once again, you start off with the potential function. Your phi x has to be the x coordinate of your field. So phi x has to be z. Your phi y has to be the y component of the field, minus z cosine yz. And your phi z has to be your z component of the field, x minus y cosine of yz. So here we're trying to find the function of three variables. So we pick one, integrate it, and then we try to find the dependence on the other two. So we either integrate, so here are the three choices we start with. Integrate phi x with respect to x, phi y with respect to y, phi z with respect to z. So which one do you want to go after first, x, y, or z? All right, we'll do the x. So phi is the integral of phi x dx. I guess I'll start this on another page. Well, phi x is just z dx. And what's the integral of z dx? Yeah, exactly. Xz plus a c. Now that c, though, is a c as far as x and y are, as far as x is concerned, which means it could depend upon who? Y and z. So now the goal is to pin down what that c function is. So to do that, we're going to now take a partial derivative. So we'll take a partial derivative, we'll say with respect to y. That's going to drop out. I would have the partial derivative of c with respect to y. And what is this supposed to be? That's supposed to be the n. That's supposed to be minus z cosine yz. Right? So I can figure out what c is now by integrating this with respect to y. So now we're sort of back into the same situation we were in the first example. And what do you get when you integrate this with respect to y? Remember, you'd be treating z as a constant. So what do you get? Yep. Minus sine of yz plus a constant. Now this constant is part of a function of y and z only, but I integrated out the y, so this constant could depend upon what? Z. So now here's what my phi looks like. It looks like xz minus sine of yz plus c of z. All right? The last piece I need is to figure out what that is. And to figure out what that is, I'm going to take the partial of phi with respect to z and see what that's supposed to be. So partial of phi with respect to z, that would give me the x for here. And then the derivative of this, if I'm taking the derivative with respect to z, what would pop out? And the derivative of this with respect to z would be your c prime of c. And this is supposed to equal the z component of the field, which is x minus y cosine yz. And so once again, I've got all these terms present and accounted for. So you're going to get c prime of z to be 0, which means c of z is just a constant. So my final answer for the potential function phi is xz minus sine of yz plus a constant. And once again, the ultimate check is you take the gradient of phi, you get the field f. So let's take a minute and make sure we're all cool with how this this procedure works. So that's one of the, when we started talking about Calc 3 at the very beginning of the course, I said the way we're going to be approaching calculus of several variables is we're going to be looking at one variable at a time. So this is just yet another instance of that. Now, there is another way to go about finding potentials where you just kind of go in there. You just integrate this with respect to x, this with respect to y, this with respect to z, and then try to match up bits and bobs. And, that's fine. When I learned it, I was presented this way, and I like it because it's pretty methodical. And by the time you get down to the end, you've kind of got the checks built into it. Okay, so who would care about finding a potential function? Well, let's kind of review here, recall. If you have a function, say, of two variables, we talked about the total differential. Do you remember what the total differential was? If your function had continuous first partials, you were guaranteed the function's differentiable. And then you could figure out the differential as a means to approximate the change in the function. It was phi x at xy dx plus phi y at xy dy. So you were taking, basically, to approximate the change in the function itself. If your function were differentiable, then you could just look at the rate of change in the x direction times the change in x plus the rate of change in the y direction times the change in y. And by just looking at what's happening in those two principal directions, you could get a good approximation for what's happening in the curve overall. That was the beauty of differentiability. Remember this? All right, so let's say you're trying to find yourself the work integral f dot dr. where your f is an mn, which is a phi x, phi y. Then we've already seen we could look at this integral as an m dx plus an n dy. So we talked about that at the end of yesterday's lesson. But if f is conservative, then m is phi x, n is phi y. So this is equal to the integral of phi x dx plus phi y dy. Which means this is just the integral of the differential of phi, which this is just the change in phi. So what I mean by change in phi, well, we'll talk about that in a minute, but there it is. In other words, the work done in or by a conservative field is equal to the change in potential. And if you're a fan of physics, you already know this. This is where it would be nice if we were in person, and but let's say you're walking around, you've got some object. You take this object and you swish it around. Maybe you go up a couple flights of stairs, move over, things like that, over to here. Okay? As far as gravity is concerned, even though you moved this thing all over the place, you went upstairs and things like that. As far as gravity is concerned, the only thing that matters for gravity is mgh. The only difference, the only thing gravity cares about is the change in its gravitational potential, which is the difference in the height. That's the only work you did against gravity, was your change in height. That's the difference in the gravitational potential. So this is big. That's the fundamental theorem, of line integrals. So here the curve C starts at the point AB and ends at the point CD. And it is directional. So you have to start here. This is your start point, and that's your end point, and that's it. Now, by golly, doesn't that look familiar to you? Have you seen this kind of thing before? What's the integral from A to B, f prime of t dt? Well, what's an antiderivative of f prime? So this is f of b minus f of a. Do you see how this is just another manifestation of the fundamental theorem of calculus? You're integrating a derivative. The result is a difference of the function at the endpoints. You're integrating a derivative. It ends up being the difference of the function at the endpoints. It's literally the fundamental theorem of calculus. In fact, if you wanted to go in there and see that more explicitly, if you parameterize C as R of t between some values, let's say TA and TB, then you could use the chain rule we had. And you could get d phi to be phi x dx plus phi y dy. That's our chain rule. Phi x would be, let's see, phi x times x prime of t dt plus phi y prime of t dt and so the integral over c of f dot dr would be the integral from ta to tb phi x x prime plus phi y prime dt, which, courtesy of the chain rule, would just be phi prime of t dt. And so if you use parameterizations, it literally is the fundamental theorem of calculus. Right? You get phi at the one endpoint minus phi at the other. So this is literally, if you use parameterization, it literally is the fundamental theorem of calculus. So a couple of things to note about this. If you have a conservative field, the only thing that's important is where the curve starts and where it stops. It doesn't matter how you go from one point to the other. You could go on a curve, you can go on a straight line, just like with gravity. It doesn't matter how you get from this altitude to this altitude. The only thing that matters is your change in altitude. You could just go straight up if you wanted to. That's the same work as meandering around. So the fact that the actual path you take from the starting point to the ending point doesn't matter means that this integral would be called path independent. It doesn't matter how you get from A to B. This is kind of like the ends justify the means. It doesn't matter how you get there. So if you're trying to calculate a work integral in a conservative field, you've got options. You can integrate it on the path they give you. You could replace it with a simpler path, like a line segment, or if you can find the potential easy enough, you can hit it with the fundamental theorem of line integrals. Let's take a quick look at example 4 here, and then we'll call it a week. Tomorrow we'll pick up, or not tomorrow, Monday we'll pick up with this. Show f is conservative and find a potential for f. So to show f is conservative, I start off with my m and my n. The m is always the x component. The n is always the y component. And to show f is conservative, I need to show that the exactest condition holds. So I'm going to take the derivative of the x component with respect to y, and the derivative of the y component with respect to x. Once again, we're checking for equality of mixed partials. So my and nx are the same. So then I would go back, phi x would be 2xy, phi y would be x squared. You pick one of these to integrate. And you'll get that as your go through the process there. We got about 5 minutes to go, so you take your partial with respect to y and all that other good stuff, and you'll end up getting that's your potential. So once you get the potential, you can find these things. You're trying to find the work done moving from 0, 1 to 1, 4. Along a directed line segment. Well, it doesn't matter. You could go any curve. Right? Any curve to get there. So the integral c f dot dr is just going to be your potential at 1, 4 minus your potential at 0, 1. The potential here we found was x squared y plus a constant. The constant's not going to matter because we're doing what? Subtracting. Just like the particular antiderivative you got. You can think of this phi here, this potential function, as being sort of a scalar antiderivative of the field. So if you take phi at 1, 4 minus phi at 0, 1, you got 1 times 4, 4 plus c minus 0 plus c, you're going to get 4. If c is the curve starting at 1, 4 and ending at 0, 1, so notice now we're going backwards. Then the work done would just be phi of 0, 1 minus phi of 1, 4. We would just get the exact opposite work we did before. Now we did know that work integrals are directional. In other words, if you look at the work done in reverse direction, you're going to get the opposite work. We knew that if we were going along the same curve C. But the fundamental theorem of line integrals says in a conservative field, the curve itself doesn't matter. All that matters is the start point and the end point. So even though we found the work moving along a line segment from 0, 1 to 1, 4, the work done coming back along that parabolic path is going to be the opposite of the work done in part A, because you're just now subtracting the opposite direction. You follow? So then what would happen if you wanted to figure out the total work done from 0, 1 along the line segment to 1, 4 and then back along this parabolic segment? Well, these two things would exactly what? Cancel out. If you start and stop at the same place, we call that a closed curve. And as long as you start and stop at the same place, the value of the potential function will be the same because it is a function. That's what function means. If you plug the same point in, you get the same value out. And so if you try to find the work done in a conservative field along a closed loop, the work is 0. So if you look at the work against gravity, if you start at the bottom of the stairs and you climb up the stairs, and then you take the elevator down, the net work against gravity is 0 because you went down as far as you went up. And so if you have a closed curve, we talked about this when we talked about circulation. We typically put a little loop on it. So that's how we talk about a closed curve, is the loop. Okay. So we'll pick up on Monday with this example. You got the weekend to kind of let this percolate and sink in. We'll talk about how to attack one of these things. I think we already talked about your take-home and your test. Your test is looking at a work integral and a mass integral for a particular curve. And then the take-home, you've got a flux integral and a lateral surface area thing to work on. Those will be due on Wednesday. Monday we'll finish up the fundamental theorem of line integrals. We got a couple more examples. And then we should have time to talk about how the fundamental theorem of line integrals connects to the conservation of energy, which is pretty exciting. Okay? All right, folks. Thanks for tuning in. Have a great weekend. We'll see you back here on Monday.